The encoding of images using combinations of just two symbols, 0 and 1, is one of computing's most incredible achievements. These images, depicting imaginary worlds that never existed except in the high technology of their time, were from a mid-90s Japanese video game called Flop on the Space Mutant. And here's an icon from the same game, displayed on the left in graphical form and on the right in hex format. This image, labeled toronto.bmp, is from a CD of testing images. I really like this one because I think you can sort of see the character of the image come through in the hex display, especially in contrast to the icons before. This video is about the bitmap image format. It's part of a series of videos building a deeper understanding of programming, where we're currently working towards creating our own executables from scratch. We're covering bitmap images today as a way to get closer to working with binary formats in general. This actually isn't the original intro to this video. The original intro was a bit more boring, but it was also a lot peppier, so I now have to shift tone quite abruptly. Anyway, if you don't care about that and you just want to skip straight to the stuff about images, feel free to skip to the next chapter. Okay, 3, 2, 1. Today we're going to be building on some of the ideas introduced in recent videos, including the ideas of hex and binary code introduced in the binary code video, a lot of the ideas from the C video, in particular how we work with collections and pointers, and all the way back to the first ODES video, we'll be building on the concept of memory as an addressable array of cells. If you've followed any of the other videos though, you'll probably have absorbed that by osmosis anyway, so don't worry too much about it. And in this video we're going to start off talking about Endianness, which is a critical concept for understanding binary formats. Then we're going to have an overview of the format itself. I'm going to demonstrate building one, and then there'll be some exercises for you as well. And to kick us off, let's look at a bitmap image. Alright, let's look at Endianness. Let's say that you have a large number that is represented by multiple bytes in memory. Endianness is the way that you order those bytes. Do you order them with the most significant byte starting first, or the least significant byte? Let me show you what this means. Let's take the number 233163518, or Odes Cafe in hex, and this number's too big to store in one byte, so we're going to have to store it in multiple bytes. So let's lay out some memory for us to organize it into. And we can break it up into bytes and store them in memory, starting with the first part of the number as we see it on the left. This is called big endian order, because the big end of the number has come first. Alternatively, and slightly counterintuitively, we can store the bytes with the least significant part first. So starting with FE, which comes at the end of the number. And this is called little endian order. So big endian, which is the way we're used to representing numbers with the most significant stuff at the start and the least significant at the end, and little endian, which works the opposite way, with the least significant stuff at the start and the most significant stuff at the end. Now it's important to note that when we're talking about endianness, we're talking about the byte order, not the order within the byte. Within each byte, we essentially always represent the digits starting from the most significant on the left to the least significant on the right. But then between bytes, we could organize it in a big endian way, with the most significant byte comes first, or the little endian way, with the least significant byte coming first. The way we represent it makes it feel like little endian is going back and forth, starting with the least significant chunk, but then each chunk is organized with the most significant digit in that chunk coming at the start. So it's a little odd. You may be wondering at this point, why bother learning about little endianness at all when big endianness is so obviously the right choice? Unfortunately, you'd be mistaken. Basically, all modern computing operates with a little endian approach. So all programs running on your computer, I can almost guarantee, will be using little endian byte ordering, and most file formats also use little endian byte ordering. So while it might be counterintuitive for us to look at, it's important to know. You may then be wondering, why did they decide to do things this way? And the short answer is, there were two approaches and they both have pros and cons, so whatever anyone decided at the time won out, mostly apart from some exceptions which we still have to deal with. I'll run you through the reasons people give though, which are varying degrees of convincing. The main reason for big endian ordering, of course, is it works like ordinary numbers that we're used to, so that would be kind of nice if computers operated the same way. So that's big endian. To show you the benefits of little endian, I'll talk through some examples. So let's say we want to add two numbers together and we're operating in a big endian machine that gets each byte sequentially. So we can add the first byte while the computer is fetching the second byte. So in this case, we add these two numbers together, we get D7, and then we get our second byte, which we can then add together. But the second byte actually ends up needing to carry a number back to the first byte. So we then have to go back, fill that in, and if this carry leads to us having to do multiple carries, we might end up having to kind of unpick a whole bunch of addition. So basically, doing addition starting from the left is kind of annoying, and it's why as humans, when we're doing addition, we start from the right. Now on a little endian machine, this works much more how we would expect. We can start from the left, generating our larger number we need to carry from, which we can then assign into memory and add into the 2 bytes we get later. So a much nicer, cleaner algorithm. One other cited advantage of little endian byte ordering is to do with casting. So let's say we have a number that has been stored in a long type, but which is actually quite a small number. So here we have a type that takes 8 bytes to store, but only 2 bytes of real information in there. Worth noting that typically, when we're dealing with numbers across multiple bytes, our variable will be pointing to the first byte in memory. So if we then want to cast or interpret this as a smaller type, say an integer, we end up with 0 because we're just going to get, say, the first 2 bytes rather than the last 2. So on a big endian machine, this isn't so convenient. Whereas on a little endian machine, because all of the least significant bytes are at the start, we can cast down to a smaller type and the number is essentially unchanged, which is kind of convenient. But there's no reason you couldn't argue that in a big endian machine, you could have your long number types point to the end of the number and then move backwards, or even with addition, you could start loading bytes backwards rather than forwards. Now that would be kind of odd in a different way for sequences to work backwards like that, so you can't really win. Certain algorithms and situations benefit from bytes going upwards in significance, and certain algorithms and situations benefit from bytes going downwards in significance. So there's trade-offs for each, and there's no obviously one winning approach, no one sort of slam dunk that makes one better than the other. So it's just been whatever people have chosen. And what we've ended up with is some situations and systems use one order, some situations and systems use the other. It just turns out that most computer processors these days have ended up with a little endian byte ordering, which is kind of handy for compatibility. But on the other hand, nearly all networking applications have ended up using a big endian byte order. So you kind of have to deal with both. So this is really critical for you to know if you're working on production applications. If you're just playing around, then you can probably just pick whichever one suits the situation you're in. And that's Endianness, the ordering of bytes that represent single values in memory. Oh, and by the way, we're talking about single values here. So if we're talking about arrays or strings, those still move forward from the start of the string to the end of the string as you'd expect. There's no fancy reordering of those. The bitmap format's actually older than me, and the documentation is a bit patchy, plus there are a few variations, which makes it kind of complicated. Mostly the process is you go and find some old arcane website with a tilde in the title where one of the old wizards has uploaded Programming Windows 5th edition, the definitive guide to the Windows 32 API, find a page which begins interestingly enough, and that, in contrast to Microsoft.com, will typically contain all the information you need, as well as a lot you don't. It's a pretty great page. Based on this, I've put together this information-dense diagram, which you may find fun to pore over. It's an example bitmap file in hex format with everything labeled. Now, this is just one possible variation, of which there are quite a few, at least 6, possibly more. But all we want right now is to create some viable bitmap files and maybe read some typical examples, and this is a fairly typical example. The bitmap file has 3 parts: the file header, the info header, and the pixel data. The file header tells you the basics, that it's a bitmap file, the size of the whole file, and the offset that we can actually find the pixels at. And if you remember little endian, this is all in little endian format, this whole file. The info header tells you the size of itself, the image width, height, something called panes, which is always 1, how many bits we're using to describe each pixel, which for us is 24, whether it's compressed, which it's not, the size of the pixel data, the number of pixels, x and y, that you should print per meter if you print it out, which you should not do because what are you doing printing out a raw bitmap image in 2024, and then some information about the color index, which we're also not using, unless you've come back here from the exercise later on, where you have to use color indexes, in which case go read that document by the aforementioned legend to find out more. After this, there are the pixels, which are in groups of 3, and you're probably thinking red, green, blue, but it's not red, green, blue, it's actually blue, green, red. And I think this is because in an RGB color, red is of course the largest color and blue is the smallest. So we should store it little endian, with blue being the smallest color coming first and red being the largest color coming last. If you want to have a bit of fun, you can download Imhex, which is a great piece of software by the way, and craft a bitmap file yourself using your bare hands. Here I am putting in the file header. I'm not quite sure how big the file will be, so I'm coming back to it. Then the info header, and finally the pixel data, which you can also see appearing on the right in my handy image visualizer. Now I also want to show you this because it illustrates a very important point. Bitmap images, much like the raw image in the human eyeball, are upside down. The first pixel in the hex editor is actually the bottom left pixel in the image, making the first row in the data the bottom row in the image and the last row in the data the top row, which is useful to know. ImHex is really good, by the way. You should definitely download it. And if you do, you can then fiddle around and see what happens if you change the size of the image in the info header to be incorrect, given how many pixels there are, which is kind of fun. This has changed some of the colors, which is kind of surprising, but also illustrates an important point about the bitmap format. To dig into this, let's make an image that's 5 by 5 pixels. When we get to the end of the first row, we end up missing a pixel, and then the start of the next row is red, and this is because I've missed an important part of the format. Each row must be padded to a multiple of 4 bytes. If my image is 5 pixels wide, that's going to be 5 by 3 bytes long, 15 bytes, so we then need to add a single byte of zeros to pad out the row to 16 bytes. Not doing this means that our color gets offset one to the left, so instead of filling data into the blue byte, I end up filling it into the red byte. So why does the format ask for this? My fairly strong guess is that it's to do with the fact that aligning data structures to a 4-byte offset makes memory reads more efficient, which is pretty crucial when a slow 80s computer reads large bitmap files. If you want to dig more into the format, you can find my diagram and a link to Petzold's document on the ODE's website linked in the description. Now we're going to move on to writing bitmap files using code. I'm going to talk you through my process writing a bitmap image encoder in C. And I'm not claiming to be like a flawless person who never makes any mistakes, gets everything right the first time. So there'll be a few mistakes and a couple instances of doubling back, particularly around sizes. So I'll highlight those as they occur so they don't trip you up as well. Now I've run you through the overall structure of the program. We've got one struct representing a conceptual bitmap, just a width, height, and a pointer to an array of pixels. And each pixel is represented by a type alias, which I've called color T, and I've defined it as an unsigned integer, which is actually my first technical mistake because the integer type in C is only guaranteed to have 2 bytes, whereas we're going to need 3 for storing each component of the color, so red, green, and blue. So really I should have used a bigger type. Still, basically every computer is going to provide us with 4 bytes for an integer, so it works in this case, just worth you knowing. We're then going to create a series of functions, 2 to create and free up the bitmap structs, 2 to draw on the bitmap so that we have something to save, and 1 function which delegates to 3 other functions to actually encode into the format and save to a file. We'll start with the init bitmap function. I'm using malloc to allocate the memory for the pixels since I thought design-wise it's nice to have that encapsulated into the library rather than leave it for a user to potentially get wrong. We get a pointer from malloc which we can put in our struct and we're done. For freeing, I knew I needed to free up the memory allocated for the pixels, especially since this can get quite large. But I then realized I'd be left with a pointer to freed memory in my struct, and ideally we'd make it impossible for the caller to accidentally use this and then reference memory that had potentially gotten reused for something else. I wasn't 100% sure the best way to do this, but Copilot recommended to use null, and I figured that made sense since at least that would then throw a really obvious fatal error rather than potentially do anything unexpected. We then move on to the setPixel function, which is nothing special, just indexes into the array and has some guards to prevent me making any silly mistakes. We're going to leave the fill function until later. Moving on to the meat of things, we start the write bitmap function. This is going to be responsible for opening and closing the file and then delegating to a few other functions. I use fopen, which for some reason in my head I call fopen for the file operations, remembering to open the file in WB mode for write binary rather than just W mode, which I gather can cause problems if you're writing binary data, though I think that might just be on Windows. Anyway, I chose WB mode. I start writing the code for write file header in line. I can use fputs to put the magic I'm a bitmap string, BM, into the file. I then set about trying to calculate the size of the file, which will be the size of the file header, which is 14 bytes, plus the size of the info header, which is 40, and then the size of the pixel data. The pixel data size is the part I'm puzzling over. It's 3 bytes times the number of pixels, but you also need to include the number of bytes of padding you've added to each row. And I get the formula wrong a couple of times before putting in an assert and checking a few values to verify that I've gotten it right. From here, I start using fwrite to write to the file. Fwrite takes 4 arguments, a pointer to a place in memory, a byte size for the item to copy, the type of item I mean, a count of items to copy in case you want to copy more than one, and a file. Because fwrite takes a pointer, we have to set up variables first to get pointers to them. This ampersand means get a pointer to this variable. This should also prompt us to realize that if we were operating on a big endian machine, this code would mistakenly copy big endian data into the little endian file format, which is what Bitmap is supposed to be. So luckily, we're operating on a little endian machine, so it all works. There are ways around this if you're implementing like a proper library, in which case you'd need to really consider that, but I didn't do any of that here because I knew which kind of machine I was operating on. I also looked in to see if there was some nicer alternative to fwrite here that avoided all the variables and pointers stuff, but I didn't find one. Feel free to correct me in the comments if you like. There are some points later on I could have used fputc, but I didn't do it, so a potential area for improvement. You can also see at this point that I've opened up a VS Code hex editor view on the right, so we can see the file build up. I calculate the offset as the size of the headers, which for us is fixed, and we're done with that, so I extract the function. I also name it without a second underscore between file and header for some reason. I think my brain is still a bit sort of hesitant over the C naming convention, so I keep doing silly things like that. So do better than me, hopefully. I move on to writing the info header function, and I realize that it might be handy to set the variables at the top and then write it at the end. I then realize when trying to calculate the byte size of the pixel data that it might be handy to extract the code I previously wrote in write file header to a utility function. So I do that, and I'm unfortunately not done going back to and meddling with that piece of code, so it'll come back later. I set the rest of the variables and then write them all out in their respective sizes. Note that they're not all 4 bytes long and some of them are 2 bytes. I move on now to the pixel data, which involves looping through the height starting from the last Y value so that we can write the bitmap from bottom row to top row as the format desires. X goes from left to right, as you probably expect. Then we need to extract the color components. We can't write them directly because we need to reverse them to get the BGR order rather than the RGB order, since Bitmap uses BGR order. To do this, we use bitwise AND to extract the part of the value that we want, first byte for red, middle byte for green, and last byte for blue. We then shift rightwards to push our desired chunk to the lowest part of the value, so it's FF and not FF00, which would be a bigger number. We do this 3 times to extract each component and then write them out in reverse order. We now have them written, though I think I could use fputc here instead. I realize now that if I'm going to write the padding for the row, I'm going to need to know how wide each row should be, which is the same logic I wrote before in the image size function. So I extract the row part of that again, hesitating slightly because I'm not really sure if image size is worth it on its own, but then I just blaze on anyway, and I write this slightly weird for loop here, but it works, so I move on. And I now have a bitmap with 1 red pixel in the top left, which is a big success. I play around with it a bit, and then I move on to implementing fill, which is fairly straightforward, though I think I make an off by 1 error because I've still not learned how to get that right after 20 years of doing this stuff. And to test it out, I make that flag that the girl with the racing missions in Cyberpunk has on her truck. You can also do all this in JavaScript if that's what you want to do. For my part, I've been writing so much C that I could barely remember what normal JavaScript looks like, so I wrote this slightly odd fusion style. The whole thing works fairly similarly. The major difference is that instead of writing to a file, we're going to write to the node buffer type. It's been sort of interesting coming back to the buffer type after playing around with buffers in C, because you can sort of see what the intent was there. You can treat it broadly the same, but it has some cool methods on it. Just make sure that you use the LE versions for little endian and the right number in the method for how many bytes you want to write. So for example, write uint 32LE will write a unsigned integer of 32 bits long, little endian style, so 32 bits being 4 bytes. And feel free to slow down this part of the video if you want to inspect any of the details or spot any of the fun mistakes that I made. For example, why did I import the promises version of the library if I don't await on it? A true mystery. This is just the beginning though, there's plenty for you to do, so let me run you through the exercises that come with this video. Every Odes video comes with its own page for extra resources and exercise, and this one is no exception. We've got the reference sheet I worked through earlier, a link to Petzold's chapter on bitmap images, and then we've got some exercises. These are here so you can get this stuff fully in your brain by tackling it practically. In the first exercise, I want you to build a bitmap decoder that will take a bitmap image and print it out to the terminal using colored blocks. And there are also some test images that you can use to test your program. In the next exercise, you'll build an encoder and some basic drawing tools so you have something to encode. There are some little tasks here for things to draw, mostly flags because those are pretty fun, although there are some trickier ones, so send them over if you make anything cool. And finally, if you want anything extra to do, there's some extra image processing tasks to do with rotating images and also working with the color in images, so black and white and extracting like the blue channel and stuff like that. Plus there's an extra exercise for members to do with the compression that's built into the bitmap format. So if you're a member or if you sign up, then not only will you get my heartfelt gratitude for supporting me to work on these videos, you'll also get a little bit of extra material with each video. And to finish, I'll show you the bitmap that I've been gradually displaying over the course of the video. It is the Olympic rings in honor of Cindy Ngamba's winning the first medal ever for the Refugee Olympics team, which was really cool to see. In boxing, by the way, definitely check that match out if you haven't. And it also serves as an extra challenge to you because while I was putting this together, I was like, it's probably not that hard. It's just 5 rings, but actually they interlock. So you can't just draw the blue one first and then the yellow one or the other way around. You've got to find a way to get them to interlock in this way. So that's pretty cool, and you might find that an interesting exercise. Thanks for watching. Let me know how you get on with the exercises and have fun.